So this video is about this kind of diagram that you need to learn how to read this week, which is a potential energy diagram. First, let's review what we talked about last week. So in order for a reaction to occur, reactant molecules have to collide with each other, and they have to collide successfully. And so if they collide with each other but they don't have enough energy, they just bounce off of each other. Or if they don't collide in like the right orientation, that's not successful. So the reaction rate depends on the energy and frequency of collision. So the more often they collide with each other and the higher their energy when they do it. Remember, energy is can be stored energy in bonds, or it could be temperature. Temperature can increase the energy, and that's going to increase the frequency of collisions, and that is what determines the rate of reaction. So increasing the temperature will increase the frequency and energy because they're moving faster and they have more energy because they're moving faster. That's what energy is, and frequency is just how often they bump into each other. Particle size, so we can increase the surface area by crushing the object or cutting it into smaller pieces, and this is going to increase the surface area and increase the frequency. You can also increase the pressure, but for gases only, and that's going to squish them together so in their smaller amount of space, and when they're in a smaller amount of space, they're more likely to react with each other. And then you can increase the number of reactants, so you can increase the concentration, and if you have more reactants in there, that's crowded, and they're more likely to bump into each other. And then you can add a catalyst, and a catalyst is just a chemical that helps, usually with orientation, helps the molecules collide with each other in the correct way, and that will lower their activation energy. Catalyst does not get you more stuff, it gets you the same amount of stuff faster. So only a very small fraction of collisions that occur in the solution lead to a reaction. This is due to two reasons. So for number one, for the reaction to occur, the colliding molecules must be oriented in a suitable way for the product molecule bonds to form. So if they bounce into each other like on the backside of the molecule, and that's not where the bonds form, then they would just bounce off of each other. And the two molecules must collide with sufficient energy to overcome the activation energy of the reaction. So the activation energy is whatever minimum energy that you need to put in order to break the initial bonds of the first chemical and then reform the bonds of the second chemical. So you got to break bonds in order to do a chemical reaction, and breaking bonds requires energy, and that's something you're going to do this week is look at that bond breaking and bond forming when you're doing a reaction. So this is what an energy diagram looks like. You start here on the left, you go up the hill, this is the activation energy, this is how much you have to put in, and then you go down the hill and this is your products here. So reactants on the left, products on the right. However, chemical reactions go two ways. Usually they can go backwards and they can go forwards. And so you can go from left to right, up and down, but also you could go backwards, so from products to reactants. So we'll talk about the forward reaction and then the reverse reaction. So forward goes this way, reverse goes that way, and slightly different energy. So you can see that the hill is smaller if I go forward than it is if I go backwards. So this one needs more energy in order to start. So let's watch a video real quick that kind of goes over some of the things you can get out of this diagram.
We've learned a lot about chemical reactions, but what is necessary for a reaction to occur on the molecular level? Collision theory states that molecules involved in a reaction, whether in the liquid or gas phase, have to collide in a particular orientation and with an amount of kinetic energy that exceeds the activation energy of a reaction. This is the amount of energy that has to be provided to allow for the reaction to proceed. Here we can see that the two molecules have to collide in a particular way in order to react. Otherwise, they will bounce right off each other. As for energy, let's refer to an energy diagram. On these, up means higher energy, and to the right means later in time. So we can see that any reaction will have an activation energy, which is the kinetic energy that the molecules must collide with in order to reach the transition state. This is the orientation which, once reached, the reaction will certainly occur. Collisions with less energy than this will not result in a reaction. From energy diagrams, we can also see delta H, or the difference in energy between the reactants and products. If the products sit lower, it is an exothermic reaction which releases energy. If the products sit higher, it is an endothermic reaction and needs to absorb energy to occur. Most people would refer to a catalyst as something that speeds up a reaction. While this is often true, the better definition is that a catalyst is something that lowers the activation energy of a reaction. Because the activation energy is lower, many more collisions will result in a successful reaction, which is why catalysis typically results in a faster rate of reaction. Catalysts do not affect the delta H of a reaction, and they are not used up stoichiometrically in a reaction. In other words, one molecule of catalyst can facilitate many reactions, unlike molecules of reactant, which are used up in order to make products. Reactions also tend to have faster rates at higher temperatures, because more heat energy means faster moving molecules, which means more kinetic energy. At higher temperatures, more individual collisions will have sufficient energy to surpass the activation barrier. So the overall reaction for many trillions of molecules will proceed more quickly.
Okay, so let's look at all of the stuff you should be able to get out of one of these energy diagrams. So see all these letters here? So A is the energy of the reactants. So right here, whatever this number is on the side here, that's A. So A is, how much energy the reactants had when they started the reaction. B is the activation energy. You usually have to subtract to get this, so it's pretty easy though. Take the highest point on the graph and where the reactants are, and subtract the highest point minus the reactants. So B is the distance that you got to get up the hill. So how much energy do you have to put in to get to the top of the hill? C is the energy of the activated complex, what comes between reactants and products. So he called this a transition state in the video as well. I'm going to call it activated complex. So it's like when all the molecules are like kind of combined, but they haven't formed their like final product yet. So the bonds have been broken, but they haven't been like fully reformed yet. Then you're here at the activated complex at the very top of the hill. It's pretty easy to find. And that's just like, once we get there, then the reaction can occur. It's sort of that state is you got to put energy to get there though, because you're breaking bonds. Then D is the energy of the products. So right here is products, but again, this is forward reaction. So this is reactants for the forward reaction. This is products for the forward reaction. But if we were going backwards, this would be reactants for the reverse reaction, and this would be products over here. E is the activation energy of the reverse reaction. So again, the reverse reaction goes this way over the hill. So starting from where we start, how much energy do you have to put in to get over that hill? That's your activation energy. And so this is the activation energy for the reverse is E here. F is the enthalpy. Enthalpy is delta H. This is also the heat created or lost in the reaction. It's like the energy in the system. So like he said in the video, if you start here, these are your reactants for the forward reaction, and these are your products. You can see that where you started and then where you ended is lower energy. So we started with more energy than we ended with. So where did that energy go? Well, it left. It left the system. So if you were holding this chemical reaction in your hand, what you would notice is by the end of it, it would feel warm in your hand, because that's the energy that is exiting the system and it's no longer in here. So energy has to be tracked just like molecules do. Energy has to be balanced. Energy, doesn't just disappear. It usually goes somewhere. So the energy tracking tells us that we started with more energy than we ended with, so we have to explain where that energy went, and it left. It radiated out as heat. So something else he talked about is exothermic versus endothermic. So this reaction here, it starts here and then it ends here. So if you end lower than where you started, then this is exothermic. So this one is exothermic. You end lower than where you started, meaning you lost energy. It exited the system. This one here, you start here and you end here, and this one ends higher than where you started. And so this one is endothermic. It sucks in energy, and so it took in more energy than what it started with. Now, funny enough, even though this is taking in more energy, endothermic reactions feel cold. So this one is going to feel cold, even though it's actually an energy sucker. It's taking in energy, and this is sometimes hard to comprehend. Like, this one makes sense. Exothermic, it lost energy, it radiated out. But endo taking in energy means it's cold, but that energy is stored in chemical bonds. It's not energy that you can feel. It's energy that the molecules are sucking up and transforming into, stored potential energy in their chemical bonds. And so this one will feel cold and this one will feel hot. And this is also something you're doing you did in the lab. You looked at exothermic and endothermic reactions, but that's stored energy in bonds. So then he talked about a catalyst. So if we have to go over this hill, we have to get to the top of this solid line, you got to put in a certain amount of energy. But a catalyst just makes that hill smaller. Everything else stays the same. So to start the reaction, you just have to put in less energy. Catalysts lower activation energy, and so the hill is like a shortened path. Remember, you start and end in the same place. Catalysts don't get you more stuff. They just get you that same amount of stuff with having to put in less energy. And if you have to put in less energy, it starts faster. All right, now we're going to do some reading of these diagrams. So does this graph represent an endothermic or exothermic reaction? So if we go back, so exothermic ends lower, endothermic ends higher. So let's look at what we got. So we are ending higher than where we started for the forward reaction. So we're starting here at 50 and we're ending at 100 and we're ending higher. So this is an endothermic reaction. If you end higher, it's endothermic, and that's because you took in energy into the system. And remember, these would feel cold, which is kind of confusing because they're taking in energy, so shouldn't they be hot? But no, they're taking in stored chemical energy. What is the heat of this reaction? That's the enthalpy. So the enthalpy, it's really important that you always do products minus reactants. Okay, products minus reactants. I'm actually going to exit this and get a pen. There we go. And let's do purple. All right, so this one here was endo. Okay. Thermic. Alright, so what is the heat of the reaction, or the enthalpy? So an enthalpy is represented by a delta H, and your delta H is always your product energy minus your reactant's energy. So it's basically like, what happened in the reaction? Did it, lose energy? Did it take in energy? What's the total reaction of the system? So it's always important that you do P minus R and not like reorder them for bigger minus smaller. So this time it's 100 is the P, and then the R energy is 50. And so this is 50. And then the unit here that we're going to use for most of these is kJ for kilojoules. So you should always put units on your answer. So this one here, what is the heat of the reaction or enthalpy? It is 50 kilojoules. What is the activation energy for this reaction? So here is the top of the hill. This is the activated complex, and so how much energy do we need to go from where we're starting here to the top of the hill? And so this one's always positive, it's never negative. 250 is the top of the hill minus where we're starting, which is 50, which means you better be able to find 200 kilojoules somewhere, maybe a spark, maybe some heat, something to put into your reaction in order for that reaction to occur. So the activation energy for this reaction is 200 kilojoules. What's the energy of the activated complex? That's easy, no subtraction. So the activated complex or transition state is right here at the top. That's when the molecules are not yet reacted, they're kind of in a clump together, and so that would be 250. So energy of the activated complex is just whatever the highest point is in the graph. And what is the activation energy for the reverse reaction? So now we're starting here, and now we have to go to the top of the hill backwards. So this time it is 250 minus 100. And again, activation energy is not ever negative. The only one that could be negative is enthalpy. So this delta H could be negative. And so this would be 150. So you have to put in 150 kilojoules in order to go backwards in the reaction here. All right. Does this graph represent an... Oh, here are the answers. Okay. Cool. Let's do another one. So does this graph represent an endothermic or exothermic reaction? So if we look here, where we start at 40 and we end at 20. So this time it's ending lower than where we started, and lower means that there's less energy in the system. So if there's less energy in this system, then where did the energy go? And it exited, it left, and exit. Okay, exit, the root for that is exo. Okay, pretty similar to each other, so this one's a little bit easier to understand. So if you end lower, they lost energy, the energy exited, and so it's exothermic. Okay. Alright, then determine the heat of the reaction, or the enthalpy. So remember, that's the delta H is the enthalpy, delta H, and it is always products minus reactants. And so products is 20, that's how much energy the products have, and then reactants is 40. And don't reorder these. I know that's gonna give me a negative number. That's fine. This number can be negative. It's the only one that's negative. Okay, and then Kj. Okay, so that is your enthalpy. It is negative 20 kilojoules, meaning that overall the enthalpy is like tracking the heat of the system. So overall we lost 20 kilojoules through this chemical reaction. Determine the activation energy. So remember, that is from where you start to the top of the hill, and this one again is always positive, so it's 100 minus where you started, which was 40, and so this is 60 kilojoules. And then what's the energy of the activated complex? That's just the top of the hill, no subtraction needed. This is 100 kilojoules. And then determine the reverse activation energy for this reaction. So reverse meaning our reactants would be here. We're starting here with C and D, and we're going to go to the top of the hill. So it is 100 minus where we started, which is 20, and then that would be 80. And again, activation energy is always positive because it's how much energy you need to put into the system, and you don't put in negative amounts of energy. Alright, so those are kind of the things that you should be able to read on a reaction diagram, and you'll be doing some practice with that later this week.